So we've been spending the majority of our time now kind of talking about acids versus bases, talking about things like pH calculations and how we can characterize and differentiate the two. It's worth noting, though, that there are situations where certain chemicals, certain compounds can actually be either an acid or a base. And these are so-called amphoteric substances, this term right here. And so it all just depends on the reaction conditions. So we all know that HCl is an acid, right? Hydrochloric acid. When it reacts with water, here's what actually happens. The HCl donates one of its protons, creating H3O plus and leaving behind Cl minus. So we would say then in that reaction that the water then is acting as a base to then react with the acid. Alternatively, if we look at something like HCO3 minus, which you might recognize as bicarbonate, bicarbonate is a base. So when bicarbonate reacts with the water, notice how it doesn't give up a proton, it actually takes a proton away from the water, leaving behind OH minus and creating H2CO3. And so in this case, the water was a base. In this case, the water was an acid. It functioned as both. And so what I'm showing you with the arrows is the movement of the proton. That's an easy way to visualize the difference between an acid and a base. So remember, acids are going to donate a proton, whereas bases are going to accept a proton. So here you can see the water is accepting the proton, thus it's a base. Here it is donating the proton, thus it's an acid. NH3 is another example that does a similar thing. We're going to react both times with water, and you might be thinking, well, wait a minute, how are these different? Well, so it's interesting. So we'll just watch what happens. Okay, based on the products alone, I want you to answer this question to yourself. Is the NH3 in this example acting like a base or an acid? And I would urge you to pay attention to the movement of the protons. And so if you said, in this case, it's acting like an acid, you would be correct. So the NH3 in this case is donating one of its protons to the H2O, and therefore it's acting like an acid. In the bottom example, you can look at what happened. Notice how the NH3 is gaining a proton to become NH4+. So that means it must have accepted a proton from the water, and because it's accepting that H+, accepting that proton, it must be a base. So you just need to pay attention to context to figure out what it's doing in that scenario, and that's another application of pH. Okay, here's a good visual of it. So this is a visual of my NH3. And so in that first example, it went from NH3 to become NH2. And so it lost one of its protons and now has a -1 charge. Whereas in the other example, it was NH3 and then it became NH4 with a +1 charge. Notice it gained an extra proton there. So other quick things just to use the terminology correctly. We can actually use some other terms, what is called a conjugate acid-base pair. And they are sort of linked by whether they donate or accept a certain proton. Okay, so just remember the acid is always the one that has the extra H+. So take a look at this example. We have HNO3, which, what's the name of that acid? I'll give you a second. It has an oxygen, so we have to think about the polyatomic. NO2 is nitrite. So ite goes to us. So this is nitrous acid. Okay, so in this case then, the nitrous acid is donating a proton to become NO2 minus. Notice the water gained an extra proton. So that is clearly the acid. This is its corresponding conjugate base. What was an acid becomes a base after it loses its proton. So these are a pair. Likewise, we can look at the water and say, in this case, water is accepting a proton, so it's a base. And once it gains that extra proton, it now has that extra proton, and so it's an acid. It's the so-called conjugate acid. So these, things are related together. All right. So just as a quick summary, stronger acids are going to easily donate protons, whereas strong bases are going to easily accept protons. Notice what I'm doing with my color scheme. Strong acids easily donate or give up protons. Strong bases easily accept or take up protons. Weak acids, on the other hand, remember, do not easily dissociate. So they do not easily donate those protons, and weak bases likewise do not easily accept. Now remember, strong and weak has nothing to do with relative danger, or even reactivity. It all has to do with to what extent does it break apart. All right? And so here's where I want to end today. We need to be able to write neutralization reactions. And these are reactions between acids and bases. If you just look at the examples right here, they sort of look familiar, or at least they should, because these actually take the form of a type of reaction we've already talked about. And hopefully right now you're thinking, oh, that's a double replacement. And you would be correct. It's a double replacement that has some specific requirements. In other words, it has to have an acid reacting with a base. And when that happens, you do have the double replacement reaction that occurs. Notice what I've done with my colors here. This H, or the two outers, are going to react with the OH to form water. And the Na is going to react with the Cl to form an ionic salt. Okay, so let's do a couple of these together, then I'll have you try a few on your own. So we know that water is going to be a product, and in this case, we know the other one is NaCl. When you do this, you're going to want to think about charges, make sure you're writing correct formulas before you then go through and balance the equation. And of course, in this case, it's 1, 1, 1, 1. Let's do another one. H3, PO4 reacting with OH minus, so we know that's going to form water. K, remember, is K plus, reacting with PO4 3 minus, and that's how we get K3PO4 and H2O. As a good tip, when you're balancing these, you can sometimes think of the water not as H2O, but as HOH, and that makes the balancing a little bit easier. So go ahead and balance this equation, and be a little careful here. It's going to be 1, 3, 1, 3. Okay, why don't you go ahead and pause the video and try the next two on your own, and then I'll go through the solution. All right, so hopefully you paused that and tried those next two examples. This is also a good opportunity to practice your naming. So H2SO4, remember, is sulfuric acid. So again, we know we're going to form water. Na has a +1 charge with SO4, which is 2 minus. And so we get Na2SO4, and then of course H2O. Balancing on that should end up being 1, 2, 1, 2. The next one, what is the name of HClO3? Give you a second to think about it. Has an O, so we're thinking polys. ClO3 is chlorate. You ate something icky, so this is chloric acid. Okay, so the aluminum is going to react with the chlorate. Aluminum is 3 plus, chlorate is -1. Have your green sheet out. Remember, you get to use that now. So the formula is AlClO3, and then of course we get our H2O. And we then need to balance our equation. In this case, it's 3, 1, 1, 3. So then these last two seem like maybe they're more complicated. I only gave you one thing. But remember, you know the other product has to be water. So then you can work backwards. Now this is a little bit trickier though, because we have to remember that water comes from HOH. So the Al is going to react with the OH portion, and the H is going to react with the Cl. So that will give us HCl and AlOH3. Again, really pay attention to your charges here. You know Al is 3 plus, you know OH is -1, hence AlOH3, and then of course we balance the equation from there. Why don't you pause the video and balance this one and then try the last one. Okay, so hopefully you had a chance to try that last one. Again, we know the other product is water. Oh, I'm sorry, the balancing for that last one was 3, 1, 1, 3. We know this one is water, so the iron is going with the OH minus, the H is going with the SO4. Iron, remember, looking at the periodic table, we don't know the charge, but we can figure it out based on the SO4. If SO4 is 2 minus, that would give us -6, which means this Fe has to be 3 plus. So we're looking at H2SO4 and FeOH3. Balance the equation, you should have gotten 3216. So what I'm going to have you do is actually look at the next assignment, but you're only going to do the neutralization reaction portion. I think it's the first 10 questions. Shouldn't take you that long, but it's good practice, necessary practice. So check that out.